Thank you for coming to my talk. The title of my talk is Multi-Rate Control Design Under Input Constraints via Fixed Time Barrier Functions. And this is a joint work done under the supervision of my advisor, Professor Dimitra Panagu, along with her collaborators at Caltech, Ryan, Dr. Hugo, and Professor Aaron Ames. So this is the outline of my talk. I'll start with the problem formulation that we studied in this paper. We'll present the contribution of our work with respect to the literature. We'll present the main multi-rate control design, and we'll finally conclude our talk. We consider a general non-linear control-affine system with bounded inputs where the input constraints are given by this set calligraphic U. And the control objective for the control design is to render this set calligraphic X as forward invariant for the system trajectories and to require that the system trajectories visit this set calligraphic X subscript T periodically. This set xt is a subset of the set X, and it is in the interior of the set defined using this another set, a calligraphic D, which is a ball of radius D for some given D. Now, to facilitate this, we define the notion of periodic safety, where the set X subscript T is called as periodically safe with respect to this set X if these two conditions hold. So the first condition is that the system trajectories visit the set X subscript T periodically with period T, and that the system trajectories always remain inside this bigger set X. There are various examples of practical problems where periodic safety is useful. For example, an autonomous robot vacuum needs to periodically dock for charging, or a solar-powered spacecraft needs to periodically reorient itself so that it can keep charging its battery. Now, the main idea to achieve periodic safety for the set xt is given here. So recall that xt is a subset of X, and it's in the interior defined using this set D. So what we do is, at the first step, we use a high-level planner to generate a reference trajectory Z, which is in the interior of the set xt, defined by the set C, and we design a low-level controller so that the two objectives are achieved. One, the overall set X is forward invariant, and two, the system trajectories come close to the reference trajectory Z at the sampling points or at the periodic times T. And this difference should always be less than or equal to a parameter C, which defines how much in the interior of the set xt the reference points were to start with. And the approach to solve this problem is making this set D here a fixed time domain of attraction for this set C, which defines how close the reference trajectory and the system trajectories are. The notion of fixed time domain of attraction is formally defined on the right-hand side. So for a given set C, set D, which contains this set C, is called as fixed time domain of attraction if for all the system trajectories starting in this set D, they remain in the set D at all times, and they also reach the set C within a fixed amount of time. So let's see how this notion is going to help us solve the problem of periodic safety of the set xt. So consider this set C1 as a subset of the set D2, which is guaranteed by design, which is something that I'm going to present later on when we present our control policy. So when the system trajectory start in C1, they automatically start in this set D2 as well. And because D is fixed time domain of attraction for C, in this case, D2 is going to be a domain of attraction of C2. It's guaranteed that if system trajectories start in D2, they are going to reach C2 within a fixed amount of time. So that's what we see here. System trajectories start here, and they reach back to this yellow set, which is C2, within a fixed amount of time. Now note that this C2 is a subset of the next domain of attraction for the next set, D3. So now that the system trajectories are starting in this set D3, they are guaranteed to reach the next required set C3 within a fixed amount of time. So this is how the system trajectories might evolve between the time intervals 2t to 3t. So they would reach this set D3. And note also that this set D, being forward invariant and a subset of set X, guarantees that system trajectories not only periodically visit the set xt, but also do not leave the bigger set X. So using this argument repetitively, what we observe is that we would obtain this kind of a periodic behavior for the closed loop system, where the system trajectories would keep visiting this interior set with a fixed period, and they would never leave the outer set, and it would be forward invariant. So to facilitate this, we define the notion of what we call as fixed time barrier functions, which combines the notion of fixed time Lyapunov functions using the literature and barrier functions using the literature separately for guaranteeing convergence and safety. Here we combine these notions because we require both safety of the set capital X, as we need the system trajectories to never leave that set, and convergence to the new set C, as we just saw in the earlier slide, within a fixed amount of time. So function H is called a fixed time barrier function for this controller point system if it satisfies this kind of an inequality along the system trajectory. And what we get out of this is that if this inequality is satisfied, then the domain of attraction for the zero superlevel set of this function H is given in this particular form, and the time of convergence for the system trajectories to reach this set is given here. So what we get out of this one function is both forward invariance of this domain D and convergence to the set C within a fixed amount of time. Now, prior work has used control barrier functions in a QP formulation to guarantee forward invariance and multi-rate control design with two different controllers at a high-level planner and low-level controller to follow the trajectory generated by high-level planner. And there has been a lot of work on this. But there are a few limitations of the prior work. So when we use only quadratic program-based formulations, these approaches, being myopic, do not guarantee that the QPs would remain feasible in future time. And when we use MPP-based schemes, it might be difficult for them to use for nonlinear systems, as it can be difficult to guarantee the recursive feasibility of these MPP-based schemes, where we might need to just assume that the MPP would remain feasible at future times. So to overcome these limitations, what we do is we combine the two approaches, where at the high level, we use an MPC scheme to generate a reference trajectory, and at a low level, we use quadratic program to follow that reference trajectory generated by the MPC planner. And we design our constraints of the MPC in such a way that the low-level controller is able to track the reference trajectory, and as a result, the MPC never becomes infeasible. So this is how the control policy looks like. Here, UL is the component coming from the low-level controller, and UM is the component coming from the high-level planner. So UM is defined using this function pi m, which is a high-level control policy used to generate a reference trajectory Z. And UL is defined using this policy pi L, which is a low-level control policy, which we use to track the reference trajectory generated by the high-level planner. Now, first we discuss the high-level planner. So in order to use MPC for the high-level planner, we linearize the system dynamics, and keeping the control input constant between two time steps, we get this discrete dynamics, which we are going to utilize in the MPC formulation. So this is one instance of MPC problem with horizon n that we solve at each discrete time step t, where the first constraint is just the system dynamics, the discretized dynamics with, where the control input is held constant. The second constraint guarantees that the generated reference points are not too far away from each other, so that the low-level controller is able to track them. And finally, the third constraint guarantees that the reference trajectory generated is in the interior of the set xt, and it's in the interior enough in the sense that it's inside the set xt O minus C, and we discussed earlier as to how it facilitates the reference trajectory for the system trajectories to track this reference trajectory and reach the set xt periodically. Now, the high-level controller is defined just as the solution of this MPP at each time step, and it is held constant between two time steps. For the low-level controller, we start by defining this HI function as this, which is what we are going to use as a fixed time barrier function. So we use this reference trajectory point ZI at time instance IT to define the barrier function HI, and note that the zero super level set of this function would be essentially the set CI, where the reference trajectory would be within the C distance from the reference trajectory. And we use a quadratic program with a flat variable delta here in the barrier function, so that it is provably feasible even under input constraints, which is the first constraint. And we use these fixed time barrier function conditions so that we have both forward invariance as well as convergence to the zero superlevel set of this function given above within a fixed amount of time. Now, to illustrate how this proposed framework really works, we perform simulation on a Segway example, whose picture is given on the top right. Here, we constrain our control input to be always below 25 units, and the high-level planner always computes our control input within 15 units. The set xt is given here. We run the MPC planner at 5 Hertz and the low-level controller at 10 kilohertz. Below, we show the evolution of the fixed time barrier function. And as we can see, within the time t, the barrier function goes to 0, guaranteeing that the system trajectories reach where they were supposed to reach in that time, and that the control input is also bounded, or it satisfies the given bound imposed on it. This figure illustrates the evolution of the system trajectories projected on the theta and pi plane. As we can see, the system trajectories might leave the set xt, but they never leave the set x. They always remain inside that. So the set x is forward invariant, and that they reach back the set xt within the given required time. This is also illustrated here in this 3D figure, where this black circle is the domain of attraction for the set C, which is C neighborhood of the reference trajectory moving forward. And as we can see, the blue trajectory, which is the actual system trajectory, it reaches the set Ci at this time instance, and then it is guaranteed to be in the domain of attraction for the next set, so that we get this periodic behavior. Now, to illustrate how this approach is better than the traditional notions, where we can simply use an exponentially stabilizing controller, here we show that a trajectory generated by an exponentially stabilizing controller might fail to reach this set Ci in the given time, so it would not reach this set. And so the MPC might become infeasible at the next time instance, because the reference trajectory and the actual trajectory would have their distances greater than the required distance in the MPC. So to conclude, we introduced the notion of periodic safety and fixed time barrier functions to achieve notion of periodically visiting a set. And we use it in a multi-rate control framework where we utilize MPC as a high-level planner and a fixed time barrier function-based quadratic program as a low-level controller. And we demonstrated that this proposed framework is capable of solving corner cases where an exponentially stabilizing controller might fail. Thank you.